In this lab, we will be observing the motion of a mass connected to a spring oscillating in 2 dimensions. These observations will then be compared to a computational model of the mass spring system. Additionally, we will be plotting the energy changes within the system utilizing a computational model. The results of this lab are important, as they can be applied to larger systems with similar behavior, such as the person swinging on a rope. Although there are a few discrepancies, I found that the observed motion of the mass closely resembled the predicted motion over the observation period. Additionally, the model shows that the system satisfies the energy principle. A fundamental principle in this lab is Newton's second law, which states that the net force acting on an object is equal to the object's mass times its acceleration. We will use this to update the velocity in our model. In this scenario, the net forces acting on the object are equal to the spring force plus the force of gravity. Another fundamental principle in this lab is the energy principle, which states that energy is always conserved, and the change in energy of a system is equal to the energy input from work done by the surroundings. In this lab, we chose the system to be the mass, spring, and earth. Since everything is within the system, no work is being done by the surroundings. Thus, the change of energy in the system is equal to the sum of the change in kinetic energy, which is the energy an object possesses due to its motion, and the sum of the change in the potential energy of the spring, which is the stored energy a spring has when it is stretched or compressed. There is also gravitational potential energy, which is the energy that is stored in an object due to the gravitational attraction of the Earth. We were given the mass of the object, which is 0.402 kilograms, and the initial stretch length of the spring, which is 0.7 meters. From tracker, we obtained the x and y positions of the mass and found the initial position and initial velocity. Using the graphs, we were also able to find the period of oscillation, which is the time it takes for the mass to complete one oscillation. In the video, it takes the mass 0.474 seconds to complete 3 oscillations in the x direction. Therefore, the period of oscillation in the x direction is equal to 1.583 seconds. In the y direction, it takes 0.4588 seconds to complete 3 oscillations. Therefore, in the y direction, the period of oscillation is 1.519 seconds. The slight difference between these two values may be due to some mass moving in an elliptical motion. However, it is important that these two values do not greatly differ, as it would result in greatly different spring constants for the same spring. Since we'll be graphing the y position in our model later, we'll be using the period of oscillation in the y direction to find the spring constant. The period of oscillation is equal to 2 pi times the square root of m over k. We can rearrange our formula to find the spring constant k, plugging in the known values. We find the spring constant is equal to 6.97 newtons per meter. Recall that in this scenario, the net force is equal to the sum of the force of gravity and the spring force. Therefore, the magnitude of the force of gravity is equivalent to the magnitude of the spring force. The magnitude of the force of gravity can be rewritten as the object's mass times the Earth's acceleration due to gravity, and the spring force, according to Hooke's law, is equal to the spring constant times the magnitude of the stretch, which is the current length of the spring minus the spring's relaxed length, represented by L0. Plugging in the known values, we find that the relaxed length is equal to 0.135 meters. To create the computational model, I first input the initial conditions of the spring mass system. The mass is set to 0.402 kilograms. Its initial position obtained from tracker is negative 0.105, negative 0.644 meters. The mass's initial velocity is 0, 0, 0, since it is initially at rest. This portion of the code takes in the mass's position data from tracker in the form of a CSV file and graphs the position with respect to time. The magnitude of the acceleration due to Earth's gravity is a constant of 9.8 meters per second squared. The spring constant in the relaxed length of the spring that was calculated earlier is then inputted. The stretch of the spring is equal to the magnitude of the vector minus the relaxed length of the spring. The L vector is calculated by subtracting the spring's position from the mass's position. The direction of the vector L, or L hat, is given by dividing the L factor by its magnitude. As discussed earlier, the total energy within the system is equal to the sum of the kinetic energy, the gravitational potential energy, and the spring potential energy. Kinetic energy is equal to 1/2 mass times velocity squared. Gravitational potential energy is equal to the mass times the acceleration due to gravity times height. Spring potential energy is equal to 1/2 times the spring constant times the spring stretch squared. This portion of the code will run until the last time step in the observations. Here, the energies are initialized. Then the force of gravity is set to 0, negative mg0. Finally, the spring force given by Hooke's law is equal to the negative spring constant times the stretch times L hat. The net force acting on the mass is then equal to the force of gravity plus the spring force. Thus, Newton's second law and the positional update formula are used to calculate the mass's velocity and position. Given the mass's new position, the length of the spring and the stretch of the spring are updated. Lastly, the change in energies in the system are calculated by subtracting their respective initial values from the final values. In the model, red represents the observed motion and blue represents the predicted motion. The observed motion closely resembles the predicted motion over the time period. However, as time increases, there is a greater discrepancy between the model and the observations. This could be due to the fact that the drag force is present, but was not taken into account. To improve results in the future, all forces acting on the mass should be accounted for. This graph displays the energy changes within the spring mass system. Kinetic energy is represented by the color blue, gravitational potential energy by red, spring potential energy by green, and total energy by orange. All the objects and interactions are described as within the system. Therefore, the work done by their surroundings is equal to 0, since the total change in energy of a system is equal to the work being done on the system. It is logical that the total energy is at a constant of 0. This illustrates that the energy principle is satisfied.